So in this video, we're going to talk about systematically how do we actually draw Newman projections, and we're going to start off at really simple molecules, and then we move on to more complicated molecules, including the eclipse versions. Now, as you guys may already learned in class, is that every molecule that we use to draw Newman projections typically have about 3 Steric conformations, as well as about 3 eclipse conformations. Right, so you'll hear generally they'll say, okay, well, every molecule that we use to demonstrate Newman projections, they have about 3 Newman projections, and that's really eliminating the eclipse versions and more focusing on the staggered version, since the staggered versions are actually lower in energy. Right, so let's do an example. So let's say you're given this molecule. Now this is actually propane, a simple alkane, and we want to draw the Newman projections. So let's start systematically. So the first thing you want to do is draw what we call you want to draw something like this. I kind of call it like an inverted Y. Now the inverted Y represents your front carbon. So please remember that your inverted Y represents your front carbon. And then you simply draw a circle in the middle of this inverted Y, and the circle actually represents your back carbon. Now, on the molecule itself, you want to be able to identify the front carbon and the back carbon. Now, this is my front carbon, so I'm going to say, and I'm going to use a difference so you can see it. Right? So this I'm going to identify as my front carbon. This will be my back carbon. So they say this is the front carbon, and this is the back carbon. Right? Now I want you to take a look at the molecule. At the front, it's a CH3, right? And so in this case, it doesn't matter where I put the hydrogen, since it's 3 hydrogens, right? So I'm gonna go ahead and fill in my hydrogens on the front carbon. So 1, 2, 3. Right? So that takes care of my front carbon. On the back carbon, I'm gonna draw 3 little ticks, is what I call them, and that represents the 3 substituents that are on the back carbon. Now I want you to bear with me here. On the back carbon, we have a CH3, and we also have 1 hydrogen, and we have another hydrogen. Right, so there goes our 3 substituents that are on the back carbon. Now, at this point, we could put this anywhere. So we could put these substituents anywhere. So in this case, I'm going to put my CH3 right here, and I'm going to put my 2 hydrogens on the other end. Now, because we're drawing the staggered version, so let's explicitly state that we're not worrying about the eclipse yet. We're going to worry about the eclipse in a different problem. This is just to get your feet wet. So we're only looking at the staggered conformations. Now, this is a plausible Newman structure for propane. Now, because we have 3 for every one of these molecules, we have 3 different staggered versions. This is how we would progress to the other staggered version. I want you to think of the back carbon as some sort of click. I want you to think of it as some sort of, it's like you're sailing on a ship, and the steering wheel, it's like a click. So you turn it once, and the boat turns. So click, click, click. So in other words, the rotations usually go in the clockwise direction. So in other words, my CH3 is going to come all the way down to replace my hydrogen, right? So my so this CH3 is going to come all the way down and replace this hydrogen. This hydrogen is now going to move and replace this hydrogen, and this hydrogen is going to move and take the CH3 place. So in other words, what we're saying is that, now remember guys, you do not touch anything on the front carbon at this place. right? So it doesn't matter in this case because the hydrogens are identical, but in different scenarios like we'll see, you just never touch the front carbon. So in other words, now my CH3 is going to be right here, and that hydrogen is going to be right there. Right? And then for the last one, I'm going to do the same thing. So I'm going to redraw the front carbon. I'm going to keep my hydrogens in the same position. I'm going to draw my circle. And now I'm just going to rotate, think of it as a click again. So now my CH3 is going to be in this position. Right? And we would say, okay, well, this is the, we would say that this is the, a representation of the three staggered versions of the propane molecule. Let's go to something more complicated where we could actually talk about the idea of torsional strain or steric hindrance, as well as the idea of a Gauche interaction. So let's say you're given, this is actually butane. And at this point, we are actually looking at we're looking at a 4-carbon molecule. Okay? And we were asked to draw the 3 staggered versions. And we're going to go to the eclipse version in another problem after this. Well, the first thing I want to do is identify the front carbon and the back carbon. So in this case, I'm going to say this is my front carbon. And this will be my back carbon. Now on the front carbon, I have a CH3 and I also have 2 hydrogens. On the back carbon, I have the same thing. I have 2 hydrogens and I have a CH3. So now we've established where what substituents are on what carbon. Now the first thing we're going to do again is draw an inverted Y. This will represent your front carbon. In this case, it does not matter where. So in this case, it does not matter where you put the substituents on the front carbon the first time you draw it. Right? So here's my CH. I'm going to put the CH2 at the top. Here's my hydrogen, and here's my hydrogen. I'm going to draw a circle and 3 little things off the circle. Now, on the back carbon, I definitely see that I have 2 hydrogens and I have a CH3. So that is the first Newman projection. And again, we're looking at only staggered. The next question that we look at, we're going to look at the eclipse, some eclipse stuff as well. All right, so this is only the staggered version we're looking at. All right. Now, remember we said that for every Newman projection, for every molecule that we do with these things, there's always 3 staggered versions. So in this case, again, we do not change the positions of the front carbon. So I'm going to keep that the same. I have a hydrogen right here, I have a hydrogen right here, and I have a CH3. Notice the front carbon does not change. The back carbon, again, is the only thing that moves like a clicking wheel. Right? Now, like we said before, think about it as moving it in a clockwise direction. So now I'm going to click. This CH3 should move to this point. And this hydrogen is going to move to this hydrogen. Right? And then this hydrogen subsequently will take the CH3 position. So in other words, what we're looking at, we should see a CH3 right here. And we should see the hydrogen and the hydrogen right here. Now, before we draw the last staggered version of this molecule, we have to talk about something. Now, notice that these CH3s are kind of close to each other, right? Look at the difference between the molecule or the Newman projection on the right versus the left. The CH3 are opposite each other, where here they're about within 60 degrees of each other. This is what we call a Gauche interaction. This is what we call a Gauche interaction. And a Gauche interaction is simply a steric interaction between two non-hydrogen groups, right? So anything that's not hydrogen, 60 degrees apart, we call a Gauche interactions. And it so happens that this actually increases the energy of the molecule, so it's not as stable as something without a Gauche interaction. So that is what we call a Gauche interaction. Now, to finish up the last Newman projection, again, I'm going to draw my front. So I'm going to draw my front carbon. Again, keep everything the same. So my CH3 was on top and my two hydrogens were here. I'm going to draw the back circle with three little things coming off it. Again, remember we said that we thought about this as a click. So now my CH3 that was right here will now move to this position. And the hydrogen that was right here is going to take this hydrogen's position, and this hydrogen is going to take the CH3's position. So in other words, what I'm looking at is my CH3 should be right here, and my hydrogen should replace them. So this is the last staggered Newman projection for butane. Now again, what are we seeing here? 60 degrees apart. Two interactions, or steric hindrance between two non-hydrogen groups, is what we call a Gauche interaction. Now, the more Gauche interaction you have, the less stable your molecule is. So again, the more Gauche interaction you have, the less stable your molecule is. So in this case, if you were given on an exam and you were asked, okay, well, which one of the molecules would be more stable, it would be this one. This one would be the lowest energy, in other words, the most stable. Or in other words, the most stable. Why? Because we do not see a Gauche interaction. The CH3, the two methyl groups, are in opposite planes, right? So there are no Gauche interactions. However, we can say that, and let's actually label these. Let's say this is structure A, this is structure B, and this is structure C, right? We can say though that B and C are equal in energy since they have both one Gauche interaction. Structure A, however, does not have any Gauche interaction, and so we would say that it would be the lowest in energy. Now, we talked about Gauche interaction, again, steric interaction between two non-hydrogen groups 60 degrees apart. Let's go into more complex stuff, right? So let's talk about a more complicated molecule in which we're going to intertwine the idea of the eclipse version of things. Now, let's say you're given this molecule. It's actually 1-chloropropane. So let's say you were given this molecule. So this molecule is what we call 1-chloropropane. We were asked to draw all the Newman projections for this molecule and circle the, in other words, the lowest energy. Right? Now, with this one, we're doing both eclipsed and we're doing the staggered conformations. Right? Now, the first thing you do again is identify your front carbon, identify your back carbon. In this case, this will be my front carbon where I have two hydrogens. Right? So this is the front. So I'm just going to write F for front. This is the back carbon, and again, we have two hydrogens. All right, but remember now we have a methyl group on the back carbon. So let's write B for back. Now, the first thing you want to do again is draw your inverted Y. Now remember, we're going to place our front carbon or substituents on the front carbon to keep it that same way throughout. Again, the front carbon does not change. So I'm going to randomly place my chlorine at the top, but I also have 2 hydrogens. All right, and we're going to keep it that throughout our drawings. I'm going to draw a back circle. Right? Now, on the back carbon, I have 2 hydrogens and a methyl group. So at this place, I'm going to place the substituents in a random order, as it doesn't matter on the first try we actually draw the Newman projections. However, we can't just change things when we go to the second one. Now, things get a little bit complicated, because now we're looking at both the eclipse and the staggered versions. Now, for the staggered version, if we were just drawing the staggered versions of the molecule, we were actually rotating. Remember when I spoke about the idea of clicking, click, click, we were actually rotating 120 degrees. Now, with the eclipse version being in the things, we're actually going to rotate 60, and then 60, and then 60, and then 60. So in other words, there's the first staggered version, as you could see. Now we're going to move the carbon chain in a clockwise direction 60 degrees. So in other words, I'm going to draw my front carbon. Again, my chlorine is at the top. My hydrogens are in the same position. Front carbon does not change. On the back carbon now, stay with me. This hydrogen is going to move 60 degrees to right here. This CH3 is going to move 60 degrees to right here. And conversely, this hydrogen will move 60 degrees to right here. So in other words, what I should see is that I should see a CH3 right here. I should see a hydrogen that's right here. And I should see another hydrogen that's right here. Ladies and gentlemen, this is the first eclipse version that we just draw. So this is the first eclipse version that we actually just drew. Now, rotating 60 degrees again, we're actually going to get a staggered version, the second staggered version. Again, the chlorine is at the top, it doesn't change. My hydrogens are in the same position. Now I'm looking at another staggered version. So 60 degrees, so 60 degrees downward, my CH3 is just going to move to about this position. So there goes my CH3, and my hydrogens are going to move 60 degrees apart as well. So here is the second staggered version of the molecule. Let me zoom out a little bit. How about the third Newman projection? Well, I'm going to draw a front carbon. The chlorine is at the top. Again, we do not change the front carbon. I'm going to draw my circle. And now 60 degrees again, we're actually going back to the idea of an eclipse version. So in other words, this CH3 is going to come to 60 degrees about right here. So there goes my CH3. This hydrogen is going to come down to about right here. There goes my hydrogen. And then the other hydrogen is going to come about right here. And that, ladies and gentlemen, that is the second eclipse version. Now stay with me. I'm going to skip lines for a second here. And now we're going to rotate again 60 degrees. So again, my chlorine is at the top again. This is the front carbon. Nothing changes. And now we're going back to a staggered version. So you could see that if we're drawing all 6 Newman projections for a molecule, including the eclipse and staggered, you could see that we're just alternating between an eclipse. So we start with a stagger, then eclipse, staggered, eclipse, till we eventually get to the 6. Okay. Now, the CH3 that was right here, it essentially is going to move 60 degrees to right there. My hydrogens are going to replace the CH3 that was essentially right here. So now we draw 1, 2, 3, 4, 5 structures, and the last structure we should expect to be another eclipse. So I'm going to draw my front carbon again. Chlorine is at the top, hydrogen, hydrogen. Now I should expect my CH3 that was right here to come down about 60 degrees right here. I should expect the hydrogens to be replaced, right? So there goes my hydrogen and there goes my hydrogen. Ladies and gentlemen, these are the 6 Newman projections for 1-chloropropane. Now let's talk about which one is actually the most stable. Let's label these. Let's say this is A, B, C, D, E, and F. So we have 6 structures in total. You should always remember that a staggered version, staggered is always lower in energy than any eclipse. So that limits her choice to only 3 options, which would make, in this case, A, C, and E. These are the 3 staggered versions. So any staggered version of a Newman projection is always lower in energy than an eclipse version. Now, A, in this case, would actually be the lowest in energy. Why? We actually do not see any interactions. There are no Gauche interactions, and there's no torsional strain. Now, speaking of torsional strain, let's talk about torsional strain. Now, remember we said that these are actually 60 degrees apart, right? And so, in fact, we do have what we call a Gauche interaction here. Okay? So this is a Gauche interaction right here between 2 non-hydrogen groups. We also have a Gauche interaction here. Right? So in structure A, we do not have any Gauche interaction. There are no torsional strain. Now, let's talk about torsional strain. Let's look at structure D. Look at this right here. Look how we had 2 non-hydrogen groups now that are actually on top of each other. And so this, guys, is what we call steric hindrance. And because of steric hindrance, we actually get torsional strain. Right? So there goes the difference. Right? So torsional strain, again, 2 interaction between 2 non-hydrogen groups that are actually on top of each other. So notice that difference versus Gauche. Gauche, they're 60 degrees apart. Torsional strain, they're pretty much on top of each other, they're essentially occupying the same space. And so we call that steric hindrance. This is what you should expect to be another Gauche interaction. 60 degrees apart between 2 non-hydrogen groups. Okay. This is another Gauche interaction, 60 degrees apart between 2 non-hydrogen groups. And so we spoke about Gauche interaction. We spoke about torsional strain or steric hindrance, or steric hindrance leading to torsional strain. But structure A again has no Gauche interactions. There are no steric hindrance. There are no torsional strains. So it will actually be the lowest energy. Also concluding that between the fact that it's also staggered, right? So any staggered conformation, like we said before, should be lower in energy than any eclipse version.